We propose a method for synthesizing novel building models from examples. These are the buildings generated using our method. And these are the input examples. They are models of real-world buildings. The synthetic models are as visually plausible as the input examples. We use Google 3D warehouse models as the input. Our system has two steps: model decomposition and parts recombination. The decomposition step partitions an input model into parts. They are shown as blocks here. The recombination step generates novel models by combining parts from the two examples. The final output model is generated by stitching together the meshes contained in the blocks. We now explain each step in detail. Our decomposition method cuts the model into rectangular blocks. The cut is shown as the red plane on the left, and the resulting blocks are shown on the right. We look for the optimal cut that minimizes the volume of the resulting blocks. For example, this is the optimal first level cut of this model. We recursively cut the model until no significant volume reduction can be achieved. In this example, the decomposition stops at level 4. Symmetry is important in many buildings. We identify symmetric parts during the decomposition process. This symmetry information will be used in the later recombination step. Architecture features, such as domes, roofs, and spires, are also important. We preserve these features by not decomposing any mesh that is a close fit to its convex hull. The next step is to combine the parts. It is easy to generate a large number of combinations by randomly selecting parts from the two models. However, not all of them make good models, so we need to select the good ones for high-quality model production. We use 4 criteria for selecting good combinations. First, symmetry has to be preserved in the output, so we filter out combinations that do not satisfy this constraint. Second, we penalize combinations that have a large self-intersection. Third, we penalize combinations that have weak connectivity. The self-intersection and the connectivity criteria combine to favor plausible combinations. Finally, we penalize small volumes because they are likely to be parts missed. By fusing these 4 criteria, we are able to rank the combinations. Here we show some of the highly ranked combinations. Some of these combinations are similar, so we only keep the distinctive ones. Some of the kept combinations are shown here. The final output model is produced by stitching together the meshes contained in each block. In practice, we use spatial adjustment to remove artifacts in the output model. For example, normalization of a cylindrical shape can result in distortions. This can be removed using local resizing. Some parts may float in the air, and we shift them down to the nearest neighbors. Any remaining part which is not fully supported has its base extruded to the ground. Here is the final output. We used an online survey to evaluate the visual quality of our output models. 100 participants were asked to compare the real-world buildings, our models, and models generated using a random combination. Each time they were asked to choose a preferable picture from the pair. Here, the left picture is a real-world building and the right picture is one of our generated models. Statistical analysis shows no significant preference can be found between the real-world models and our models. It also shows significant preference has been found on our models over the randomly combined models. Our method can also be used for style morphing between two buildings. Here we show different stages of the morphing from the source model towards the target model. Here is another set of results. We conclude this video using a set of buildings generated with world-famous cathedrals, such as the Florence Cathedral, the Notre Dame in Paris, St. Paul's Cathedral in London, and Sagrada Familia in Barcelona. Only the golden models are the real-world cathedrals. The grey models are generated by combining the golden models with other real-world buildings. More results can be found in another video submission. Thank you for watching our video.